Welcome to Fundamentals of Artificial Intelligence. In today's lecture, we will look at constraint satisfaction problems. Constraint satisfaction is another way of solving problems in AI, where the main idea is to get to the goal state by satisfying a group of constraints. Many problems can be posed as constraint satisfaction problems, and off-the-shelf algorithms or constraint satisfaction problem solvers could then be used to get to the solution. While we were doing state space search, we explored the idea that problems can be solved by searching in a space of states. In such a situation, these states can be evaluated by domain specific heuristics, and we tested to see whether they are goal states or not. Most of these states that we explored or we have looked at in problem solving as state space search, we can think of each state as a black box, which is assessed only by problem specific routines: the successor function, the heuristic function, and the goal test. In contrast to that, in constraint satisfaction problems, we examine problems whose states and the goal test itself conform to standard and structured representation. Such a representation then allows search algorithms to be defined that take advantage of the structure of the states and then use general purpose rather than problem specific heuristics to enable solution of large problems. Formally, a constraint satisfaction problem is a three-tuple: the set of variables. Each variable has a non-empty domain of possible values. A set of domains. Simplest kind of CSP involves variables that are discrete and have finite domains. Then we have a set of constraints. Each constraint is a pair. S1 is called the scope of the constraint and involves some subset of the variables. Ri specifies allowable combination of values for that subset. A state of the problem is defined by an assignment of values to some or all of the variables. A solution to a CSP is a complete assignment that satisfies all the constraints. A complete assignment is one in which every variable is mentioned, and an assignment is said to be legal or consistent if it does not violate any constraint. A solution is a consistent complete assignment. Now, let us look at a very popular problem from AI that uses constraint satisfaction problem solving technique, the n queens problem. The n queens problem is a problem of placing n chess queens on a n cross n chess board so that no two queens threaten each other. For example, if we are talking of the 4 queens problem, we have 4 queens to be placed on a 4 cross 4 board, and we will mark these variables as x1, x2, x3, x4, and we have 1, 2, 3, 4, the different rows. Now, how do you specify constraints in such a scenario is that the constraints could be explicitly mentioned. Like if we start with a queen here and look for what could be the position of the second queen, so we will specify a constraint between 1 and 2, then a queen cannot be here, a queen cannot be here, but we can place a queen here. So, that is what we are looking for, and therefore, a constraint that says 1 and 3 is satisfied between 1 and the first and the second queen could be explicitly stated. So, we have 1 and 3 here. Similarly, we could include 1 and 4, and then we could think of the second row for the first queen, and then the positions that could be possible is also not this, as the only position that would be possible is this. So, we could explicitly state that and include 2, 4 here. We could then think of going for the third one, in which case this also is not possible. The only possibility in the third case is having a queen there, and therefore, we would explicitly include 3, 1 to be there in the set of R, 1, 2. Here 1 and 2 refers to the first and the second queen, a relationship between them. Thereafter, we could look at the fourth row and see that these possibilities do not exist, that I cannot have a second queen here, I cannot have a second queen here, but I could have a second queen at 4, 2, which is marked there, and I could have a second queen at 4, 1, which is marked here. So, as we see here, we could state the constraints that I want between the first and the second queen as an explicit list, and this list is the list of allowable values between the first and the second queen. Similarly, I could look for values that would be possible between the first and the third, the first and the fourth, the second and the third, the second and the fourth, and the third and the fourth variables of these 4 queens problem. An assignment A bar over a scope S satisfies a constraint C if Si is a subset of S. That means that every variable in the constraint has a value, and a projection of that assignment over this scope is a subset of Ri. Now, we need to take a minute and try to understand what we mean by a projection of the assignment. So, let us go back and look at our 4 queens problem once again. We could have a queen at the first position. The second queen that I can place is definitely either this or this. So, I could place at 4, and the other queen now at position second for the variable x3 is what I can place. So, this assignment could be written as 1, 4, 2. Now, if you look at this assignment and if you look at the constraints that I was talking of and look at the queen 1 and the queen 2, then I could see that I have 1, 4, which is a possibility included in R1, 2. Similarly, if I had written the other constraints, I could have seen that I could have covered the possibility of having 4, 2 between 2 and 3 as well. An assignment is said to be consistent if it satisfies constraints in its scope. Like in the previous example that we were looking at, where I had an assignment of 1, 4, 2 for 3 queens placed on a 4 cross 4 grid, I could see that it satisfies the constraints, and therefore, that assignment is said to be consistent. An assignment that does not violate any constraint is called a consistent or legal assignment. Now, this is interesting to note here that consistent assignments may not lead to a solution. Let us look back at this example one more time. We have queen at this position, which is perfectly okay with queen at 4 for x2 and queen at 2 for x3. But when we want to have a queen for the fourth variable, we are unable to have a queen here, we are unable to have a queen at the second location, neither in the third row nor in the fourth row. So, we are not able to arrive at a solution even if initially this assignment up to the third queen was consistent. Such an assignment is called a partial assignment or a partial solution. A partial assignment is one that is an assignment only to a subset of the variables. In this case, we could assign only up to x3 and we could not do for x4. We look at another example from constraint satisfaction problems called the map coloring problem, which is about coloring each region of a map in such a way that no neighboring regions have the same color. So, here if you notice, we have 1, 2, 3, 4, 5, 6, 7 variables, and let us say we are interested in coloring them in either of 3 colors. So, we would have a domain of 3, red, green and blue. Now, if we look at what is the constraint for this problem, the constraint for this problem is that any 2 adjacent regions must have different colors. So, if you look at the first 2, let us say this is 1 and this is 2, the possibilities could be that I could have red green or red blue or green red or green blue, blue red or blue green. Now, this is how explicitly we could state the constraints, or we could state what is allowed and the rest of the things are not allowed in mapping the regions 1 and 2, map coloring them 1 and 2. So, here is a solution for the map coloring problem where we could have every region colored different. We will come back to this in our course of discussion today. Now, depending on the types of variables, we could have varieties of constraint satisfaction problems. The most common of them are the ones with discrete variables. So, they have finite domains. The Boolean CSPs, including the Boolean satisfiability problems, are of this nature. We have infinite domains, domains that have integers, strings, etc. For example, the job scheduling, they need a constraint language, and linear constraints are solvable, non-linear are undecidable. Then we have continuous variable constraint satisfaction problems, where for example, the start and times for the Hubble telescope observation. Linear constraints are solvable in polynomial time for such CSPs. Varieties of constraints may be possible. We may have unary constraints, constraints that involve a single variable, or we may have binary constraints, constraints that involve pair of variables. For example, here I have a constraint between x and y, and the sum of x plus y must be less than 6. Binary constraints can be represented by constraint graph. Then we could have higher order constraints, constraints over 3 or more variables. Now, it is interesting to note that we can convert any constraint into a set of binary constraints. They may need some auxiliary variables to be introduced. The fourth type of constraint that we could have are called preference or soft constraints. Things like we could have constraints stating red is better than green. They are often representable by a cost for each variable assignment. As I was telling you, binary constraint satisfaction problem is one in which each constraint relates at most 2 variables. We could create a constraint graph where nodes correspond to variables and arc corresponds to constraints. Coming back to the map coloring problem here, we had 7 constraints 1, 2, 3, 4, 5, 6, 7, and we could draw a constraint graph here to represent relation between the variables on the constraint graph. Each of the nodes corresponding to the variables. General purpose constraint satisfaction problems use the graph structure to speed up search. We will look at this in one of our lectures. While we are talking of higher order constraints, let us focus our attention on a very interesting crypto-arithmetic puzzle. Crypto-arithmetic puzzles are puzzles where you write things in letters and operate using mathematical operators and expect that each letter, if it stands for distinct digit, we can find some substitution for the letters in terms of the digits such that the sum is arithmetically correct, with the added restriction here that this leading letter should not have a 0. When we are trying to solve such problems, we can see that this small problem of saying 2 plus 2 is 4, we have 6 variable constraints for the above example. This literally means that all 6 letters that we can think of, T, W, O, R, U and F, are together in a constraint. And the constraint is that all of them needs to be a different digit. The addition constraints on the 4 columns of this puzzle, 1, 2, 3, 4. The 4 columns of this puzzle, they also involve several variables. All of these create a higher order constraint and they could be represented in a constraint hypergraph. So, here is the crypto-arithmetic puzzle 2 plus 2 4. On your right is the hypergraph. We could see that the 6 variables F, T, U, W, R and O are all together constraint, and this C1, C2, C3 are the carryovers possible at these columns. So, when we want to solve them, this could be like 6 placeholders, and I could have 4 placeholders for the answer, and I could have these placeholders for the carries. And the constraint hypergraph for this problem shows both the digit constraints as well as the column addition constraints. The constraint that all of them needs to be different digit is coming from this square box, and the constraint that F and C3, if this is the carryover C1, carryover C2 and carryover C3, if you remember, this was F. So, the constraint between F and C3 is coming here. C3 and F have a constraint. Similarly, and C2 as well as O here have a constraint. So, T, C2 and O have a constraint, so on and so forth. So, the constraint hypergraph for the crypto-arithmetic problem shows the digit constraints as well as the column addition constraints, and each constraint is a square box connected to the variable it constrains.